Thanks for the introduction. This talk is joined with Yuhao from Peking University, Yuhao from Columbia, and Zichen from Peking University. Both of them are also in the audience, and the authors also include Eileen, she also from NYU, and Xiaotie from Peking University. So to start with, let's have a quick look at the background about MEV and the graded sequencing rule. So MEV mainly happens in the field of decentralized finance. Where it provides some financial services in the world of blockchain. And with the smart contract, we can write down the financial rules in the form of codes and then set it up on the chain with a state here. And after that, everyone can use this financial service and with a transaction. And this transaction will change the state when it's also included in the blockchain. So decentralized exchange or CDEX is a typical class of DeFi applications. So it allows the user to exchange their tokens without the centralized authority. The trading price is automatically determined by the algorithm, which is usually a constant function. So for example, Uniswap uses the constant product function as a market maker, and it allows the user it allows the exchange between any two ERC20 tokens like the Ether and USDC. This pool is managed by a online smart contract with the state, which keeps the current results of both tokens in the pool like X and Y. And the constant product means that the product of these two values should remain constant before and after a transaction. So for example, suppose that there is 10x and 30y in the pool, and I want to swap 20x. Then it will change the pool to a new state with 30x and 10y, which means I will receive 20y with the price of 20y by 20x, which is 1. And in practice, not all of my input will be used for the swap. So suppose that I want to put into delta x Ether for some USDC, and a small fraction like here, f times delta x will be used by will charged by the Uniswap pool as a swap fee, and this swap fee will be distributed to all liquidity providers to incentivize people contributing their both tokens in the pool. And just like the gas fee, this swap fee is also the cost for the miner to have its transactions executed in the blockchain. And after I create such a CLX transaction, it will go into the public mempool and compete with others, waiting to be selected and ordered in the block by the block builders. And recently, it's found that the block builder could do some strategic behavior to extract some additional value from the block contents, except the traditional block rewards and transaction fees. So for example, after seeing there is a swap transaction in the public mempool, the block builder could front run a transaction with the same direction, and also back run a reverse transaction to sandwich this user's transaction. And in this way, the block builder could extract some profit by buying low and selling high, and it can be understood as a riskless arbitrage, but it's totally at the cost of the users because this transaction should have been executed at a better price. In practice, this behavior is feasible in blockchain because the miners has the power to manipulate the block contents. So this additional value is known as the MEV. And besides the sandwich attack, there are many other MEV behaviors like from running, liquidation, and extra. According to the data from Flashbots, since early 2020, the MEV value has been over $1.2 billion. And besides it, it also caused the problem like network congestion, high gas fee, validator centralization, and the risk of consensus instability. And to solve this issue, one of the methods is the trusted relay services services like the flashbots. So the main idea is that instead of just broadcasting your transactions into the public mempool, you can just send your transaction to us through a private channel. And our block builders will help to process your transaction. And we promise that we will never front run your transaction. So it sounds good, but the problem is it's not credible because we have no idea whether the flashbots has followed their promises. So mainly motivated by this, Flera and Parks proposed the concept of verifiable sequencing rule. The main idea is I can trust you unless you use a verifiable sequencing rule to order my transactions so that I can verify if you have followed your promises. So given a set of transactions, the sequencing rule will map it to a set of sequence that satisfy this rule. And we see a sequencing rule is verifiable if and only if there exists a algorithm such that given any order, this algorithm can verify if it follows the rule in polynomial time. And specifically, the authors propose a specific verifiable sequencing rule called the greedy sequencing rule. And here I will use an example to elaborate it. So suppose that we are facing a set of user transactions. Some are willing to sell X for Y, some are selling Y for X. So before order them, we need to check the on-chain information, and so that we can know how the country results of both tokens in the cross-bounding pool, like X0 and Y0. Then we need to take this state as the initial state and also map it to this x-axis. And then the greedy sequencing rule is that when we order the transactions, if at any time we are starting at this initial state, we can randomly pick a sell X transaction or sell Y transaction. Both directions work. So for example, now we just randomly pick up a sell X transaction. Then it will change the pool to a new state with more X and less Y. Then the next one should be a sell Y transaction, because for now, the price of selling Y is better than the initial state. It will benefit the sell Y users. And again, we are also on the right of this initial state. So the next one is also should be a sell Y transaction. And we come to the left, and then the next one should be a sell X, because at this time the price of selling X is better than the initial state. And just like this sell X, sell Y, sell X, and sell Y. So in this time we come to the left again. So the next one was supposed to be a sell X transaction, but we can find that there's no more sell X transaction. So we can just order the remaining sell Y transaction one by one. So in a summary, the greedy sequencing rule is we need to take the initial state as a baseline and then order all transactions to make them move back and forth around this line. Except that maybe in the end, there is only one type of transactions remaining. So this rule kind of mitigates the sandwich attack. But the problem is MEV is still possible. So it motivates us to think, for the miners, what's the optimal strategy to maximize their MEV? To answer this question, we mainly consider the swap transactions index, which utilize the constant function like constant product, constant mean, constant sum, and extra. And our analysis are applicable to all CFMMs satisfying two axioms. The first is, if there are more X in the pool, there should be less Y. And the second one is, with the increase of the X token, its marginal exchange rate should be decreasing. In other words, the more X in the pool, the less valuable it will be. So we can find these two axioms are very basic. Almost all CFM satisfy them. Then this swap transaction can be divided into two types: sell X or sell Y. And this here, the Q is the amount of the token to sell. And when we face these transactions, the miner could include, exclude, and reorder the transactions in the block to extract some additional value. In other words, given a set of user transactions, the miner could do three things. First, it can create some new transactions. And second, it can select a subset from all of them. And third, it should compute an order for these transactions. Then given such a strategy, the miner may obtain 5x and 5y in the end. But for another strategy may use 1x and 10y in the end. So in order to compare in order to make the results on the different strategy comparable, we define the utility of a strategy as the value of the final token holdings. And the value of a token is measured by its price, which is assumed to be exogenous. It means that the miner could have some off-chain information, or just the PX and PY. These two prices are just its own belief. And in addition, we assume these two prices is fixed during the 12-second attack. And in this talk, we assume the marginal exchange rate of the X token is exactly PX by PY, and for the Y is PY by PX. So what this function does is to enumerating all miners transaction in the final order. And this transaction is either selling X or selling Y. So suppose it's a sell X transaction, then the miner should pay some X and obtain some Y. Then the first part will be the value of the X token it paid, and the second part will be the value of Y it obtained. Then this their sum is exactly the utility of this sell X transaction. And after enumerating all these miners transactions, we could know the exact profit of this strategy. So the miner's goal is to find a strategy to maximize its final utility. So for this problem, we have two main results. First, if there is no swap fee in the pool, then we propose an algorithm to find the optimal strategy. But if the trading fee is larger than 0, then we prove it's NP hard to find such a strategy to find the optimal MEV. So first, let's look at the first case where is no swap fee. For this case, our algorithm is also greedy. Here, I also use the aforementioned example and the orders they were executed. For each user transaction, we will do two things. First, execute it at the initial state, and then insert a new transaction with the different direction to go back to the initial state. And then we just repeat these two things for each user transaction, like this. Repeat. Yeah, we can find that this strategy exactly follows the greedy sequencing rule. And for this, to prove that is optimal, the point is when we execute a transaction, we should not only consider how much utility I have obtained, but also the potential utility I could obtain later. So for the latter, we define a potential function to measure it. This function will map a state to a real value, or to a real value no less than 0. So suppose that the current state is S, where the current reserves are X and Y, then its potential value is the value of these two tokens at this state minus the value of tokens in the initial state. And then we can find for the initial state its potential value is 0, and for others is positive. And actually this phi can be understood as the potentially profitable value when we are in the state of S. And suppose that there is a transaction executed at the state S and then ends at the state S prime. It will change the potential value from phi to phi prime. And at the same time, the minus utility will also change from U to U prime. So a key observation is if the transaction is from the miner, then we have U plus phi equals U prime plus phi prime. It means that if we treat the current utility and the potential utility as a whole, then their sum will not change after a miners transaction. But if it's from the users, after this transaction, the current utility of the miner will not change, but the potential utility may change. It may increase or decrease. So combine these two things, what we need to do is to take advantage of all users' transaction to increase this phi value as much as possible. And we claim that the maximum value of this phi improvement is taken when the transaction is executed at the initial state. And we define this value as the transaction's arbitrable profit, or AP. And further, we prove that given a set of users' transactions, the miners' profit will be upbounded by the sum of all users' AP. Yeah.
Excuse me, I have a question on the way you define the transaction state. Is that changing the transaction fee change the state as well, or a state change in the previous slide is just for changing from waiting to confirm in the pool?
Oh, it means that, okay, suppose that there is a set of transactions, we know the initial state, right? We can check the state from the on-chain information. And then
Yeah, I wanted to know which criteria is mentioned for like the definition of a state. How do you define the state of a transaction?
The state of a transaction?
Yes.
Oh, it's the state of the pool. Here, the S is the state of the pool. We can find, okay, the current results of the, okay, maybe we will execute some transactions. And then at this state, the current results of both tokens will change, right? Because of these transactions. And here, the state is about the current state of the pool.
Yes, because users can update their transactions or like updating the fee. I was curious to know if this is changed the state in your model or no.
Sorry, could you repeat?
Maybe I can ask later. I do not want to interrupt yours. Yes, thank you.
Yeah.
Quick question. Is your X0, Y0 initially consistent with the X and Y? Yes?
Yeah.
Okay, and then second question, do the transactions have slippage limits attached or no?
Slippage tolerance, yeah.
They do?
Yeah.
Okay, so if you, depending on how you order them, some of them might revert, right?
Actually, the greedy sequencing rule, under the greedy sequencing rule, this thing will not happen.
Okay.
Because, because, thank you. Maybe we can, I just said that the upper bound will be the sum of all AP. And we can check that this strategy exactly reached the upper bound, right? Because each user transaction is executed at the initial state. So it means that the miner will obtain the optimal MEV. But it's very interesting that this strategy is also good for the users in at least two senses. So first, we can see that all user transaction has been executed, which is not always true if the miner takes another strategic behavior. And second, each user will obtain the profit as good as if it's the only one in the block. So here, you may be thinking, how come this happen? Because if there is no swap fee, the interplay between the miners and users is kind of the zero-sum game. So how come everyone is happy? In fact, if we look back at the results under the when the miner honestly behave, we can and compare it with the results under the optimal MEV, we can find that actually some transactions can be executed at a better price. And it means that these users could have been happier than under the optimal MEV results. But on the other hand, we should also notice that some transactions were executed at a worse price, just like the last two sell-by transaction. So in general, for the users, it's not bad when the miner takes our optimal strategy, because everyone is executed at the same initial state.
So just a sort of slight follow-up question. Does your method go through if the prices are not consistent with the initial state?
The price, sorry?
So you had PX and PY consistent with X0, right? So for example, in Uniswap V2, that would mean Y0 over X0 equals PY over PX, right? Or maybe I got something reversed, right?
Yeah.
So suppose the prices are not consistent with the initial state. So that there's DEX-SEX arbitrage possible also. Would the algorithm be always move it to the prices, the state consistent with the prices, or would it be different? Or
thanks for your question. Yeah, it's a very good point. I think maybe it's more practical. Yeah. So okay, your question is maybe the miner's belief is not the same as the initial state. So on this side, I didn't prepare it in this talk, but I can answer this question. Actually, our algorithm still works, but we need to do some modifications. The first modification is we should take the miner's belief as the baseline. I mean the potential value of that state should be 0. So we need to modify the potential function, right? And the second one is, before execute a minus transaction, we should to see the AP of this transaction is larger than 0, or maybe it's negative. So suppose it's positive, we will execute it at the initial state, or otherwise we do nothing. And the third modification is for the last step. So here we will not go back to the initial state. Instead, we will go back to the minus belief. So this is the 3 modification we need. Yeah. Thank you for the question.
Sorry, wouldn't you just arbitrage the entire thing to wouldn't you just arbitrage the entire thing to the external market price instead of making it the initial state? And then if there's not enough trades to get you there, you just wouldn't do anything. You would just include them. For the case where, because the profit you're gonna get is at the end of the block, right? So you would just arbitrage to the end of the block's price, which because you're in the miner and you're gonna put it on immediately.
Yeah, for the inner transactions is go back to the initial state just like before, but we only go back to the minus belief in the last transaction. For the last transaction.
All right.
Yeah.
Thanks.
Thank you. Okay, maybe let's see the second setting that the trend.
Check the other slide. Just one back. My only comment here would be that assuming that X reserves is on a price line, that's actually not the optimal MEV. That's probably the best experience that every or price experience that every buyer or seller will see. The optimal MEV would be to aggregate and actually not backrun any transactions in which the transaction order flow is going in the same direction twice. The 2 green arrows would go one after another sequentially, and then you would backrun it back to 0 because the gain would be greater. There would be more MEV because the price arguably would be cheaper to buy.
Yeah, but it doesn't follow the greedy sequencing rule, right? Because after the first transaction, the next one should go back to the initial state. So we cannot execute them in the sequence.
Okay.
Yeah, it's under the greedy sequencing rule.
Okay.
Thank you.
Would it change the order of the transactions? Just went back on every single one.
No, the point is that you're required to do that, right? That's the requirement of there.
Yeah.
We can keep the rest of the questions until.
Yeah, I can. Okay, so fast. Yeah, for the second case, there is this arbitrage-free interval. It means that for any transaction executed in this interval, the its potential value, its utility will be negative. So based on this, we define all the potential value of all states in this interval as 0. And for the others, we need to do some modification. Basically, it's for the states on the left, we need to take the left boundary as the benchmark. And for the states on the right, we need to take the right boundary as the baseline when define the potential value of a state. Despite this modification, the definition of AP is exactly the same, and we can also prove that the miner's profit is also upbounded by the sum of the AP. But very unfortunately, it's NP hard to reach the upper bound. And actually, we can reduce the partition problem to this MEV optimization problem. Here, maybe I will skip the details of the instant construction. Yeah, there are. So finally, there are also some open problems. First, although it's NP hard for the miner to extract the optimal MEV when there is some trading fee, but it's also worth to design a polynomial algorithm with a good approximation guarantee. The second is about the strategic analysis from the perspective of users. So recall that all user transactions will be executed at the initial state. Then a better strategy for the user is to split its transaction into several smaller ones. In this way, it can obtain better profit. So a question could be, what's the optimal strategy for the users? And if all users are rational, what's the equilibrium? And the third question is about mechanism design. Our analysis provides some support for the further research on the further study of the sequencing rule. Then a critical problem is how to measure different sequencing rules and what's the optimal design of a sequencing rule. Yeah, I think my talk will end here, and thank you. Thanks for
perhaps one or two more questions from the audience.
Quick question. So this seems very nice in the case of when you have a single market, but how does it generalize to when you have multiple markets, and therefore there's kind of an open ordering question, right? Like now miners can actually order transactions because they're not necessarily directly comparable if they come from separate markets with separate prices. So like, let's say we have like A to B, B to C, and C to A, right? Like any one of them might have consistent ordering over the kind of the trades and the directions they go, but it's not obvious when you kind of have many trades, like what that ordering actually is. Does that make sense?
Yeah, so, I think it makes sense, and it's a good point.
I asked because the Ferreira and Parks rule has the same problem too, which is they sort by prices, but the notion of prices only makes sense when you only have like one single asset. Otherwise, you have to consider like multidimensional prices. And so things are kind of funky. I don't know if you've thought about it. I'm just curious.
Yeah, maybe we can talk later. Yeah,
thanks.
So how do you consider external factors having like different emission states to go back to? Because yeah, you can everything's like independent, but it's one. So it's well defined strategy and so on. But when you consider external factors and adversaries and factors, it's completely different. Yeah, going back to the emission state, I don't see how this applies to having several markets and so on. Thanks.
Yeah.
Maybe it's the question. I don't know. We can discuss offline or something, but yeah, it's a very interesting test.
Yeah. Maybe later we can talk about that.
Thanks a lot.
Yeah. Thank you.